A disk is initially rotating counterclockwise around a fixed axis with angular speed omega naught. At time t equals 0, the two forces F1 and F2 shown in the figure are exerted on the disk, with F1 greater than F2. For part A, we want to describe as completely and concisely as possible the motion of the disk after the two forces begin to act on it. So, this is rotational motion, but we can basically treat it the exact same way that we treated translational motion. So if you think about this, the initial angular speed is counterclockwise, which is positive. Remember, counterclockwise is positive, clockwise is negative. So let's think of this as an initial linear speed in the positive direction. So we have some kind of, maybe like a box on a surface, and it has an initial speed VO, positive direction. Now you're having these two forces that are acting on this disk, and those two forces create a torque. So the torque of this force, which is pulling it clockwise, is greater than the torque of this force, which is pulling it counterclockwise. So remember, clockwise is negative, counterclockwise is positive. So you have a bigger negative torque than a positive torque, so the overall net torque is negative. Thinking of that in terms of forces on this figure, it's kind of like saying you have a large negative force. So I'll draw like an F1 in the negative direction that is bigger than the F2 in the positive direction. So what that means is, even though the block was initially moving toward the right, we're applying a force to it where the net force is to the left. This has the initial velocity that is counterclockwise, but we're applying a torque to it where that net torque is clockwise in the opposite direction. So what would happen in this situation? Well, if the object was moving to the right, but you apply a net force to the left, that net force is going to cause the object to slow down until it stops moving, and then it's going to reverse direction and start speeding up in the direction of that force, of that net force. The same exact thing happens with this, only in rotational form. It's initially rotating counterclockwise, but due to that net torque in the clockwise direction, it's going to slow down until it reaches 0, and then it's going to start speeding up in the opposite direction, in the clockwise direction, and we'll just keep speeding up. So that's your best way to answer part A, is kind of related to the linear motion to figure out what's going on in the rotational motion. Now part B, if the two forces continue to act on the disk, is it possible for the magnitude of the angular velocity at some point in the future to have the same magnitude as the initial angular velocity, omega 0? And we said that, so with omega 0 being that initial velocity, it's the same like having the V0 or the V naught right here. The net force to the left is going to cause this to slow down until it reaches 0. Then it's going to reverse direction and start speeding up. So if it's speeding up from 0, at some point that speed, or the velocity in the negative direction, is going to have the same magnitude as whatever the starting speed was. And the same thing happens right here. If this thing has an initial angular speed that is counterclockwise, but the net torque is clockwise, that's going to cause it to slow down until it stops, then reverse direction and start speeding up, and at one point the angular speed, or the magnitude of the angular velocity in the clockwise direction, will be the same as the magnitude of the angular velocity that it started with. So yes, it is possible to happen. Okay, part C, let's draw some graphs of the motion. And again, let's look at the linear case of this. So instead of plotting omega versus t and, and alpha versus t, I'm going to plot v versus t, the linear velocity versus t, and the a versus t, and just see how they compare. So for the acceleration, let's do the acceleration graph first because it's easier. Because on this diagram, the net force is to the left, which is negative, there's going to be an acceleration to the left, which will also be negative. And that acceleration is going to be constant because these forces are constant. So you're just going to have a constant negative acceleration on that graph. And for the velocity graph, the velocity initially starts out positive because it's moving to the right, but we said it's gradually going to slow down until it reaches 0, and then it's going to have a negative velocity that's gradually increasing in magnitude. So that one will start out with a positive velocity, so up here somewhere, gradually going down to 0, and then once it gets to 0, now it's speeding up in the negative direction, and it will just keep on going as long as those two forces act on it. These two graphs give you basically the same exact thing that would happen if I plotted, instead of that V, if I plotted omega, and instead of that A, if I plotted alpha. Because on this diagram, the net torque is clockwise, which is negative, and the net torque will lead to an angular acceleration. And since that net torque is constant, the angular acceleration is constant. It's constant clockwise, which is a constant negative, just like this one. And for the angular speed, it's initially counterclockwise, which is positive. It's slowing down until it reaches 0, and then it causes to reverse direction, so now it's increasing in the negative direction. And finally, part D, identify an aspect from one of the graphs in part C that provides support for the answer chosen in part B, about is it possible for the magnitude of the velocity, to be, the angular velocity, to be the same. But we can't really tell a whole lot from this graph because it's just that horizontal line. But if you look at this graph, the starting value up here was that omega 0. So we just need to know, is it possible to have the same magnitude, which would basically be a negative omega 0. And since this graph will just keep on going indefinitely, as long as those torques apply to it, eventually it has to cross a point where it is negative omega 0. So just the fact that it crosses that horizontal line of negative omega 0 is enough support to say that it will have, at some point, have the same magnitude that it started with.